Bismillahirrahmanirrahim. I am Dr. Muhammad Adnan, working as Assistant Professor in the Department of Physics, Kohat University of Science and Technology. I welcome you to the course PHY 352 Nuclear Physics 1. Today it is the 15th lecture of this course and the topic is nuclear quadrupole moments. First, I will give the learning objective. At the end of this lecture, the student will understand how the nuclear quadrupole moment arises in various nuclei. If you remember, in the first part of this course, we have discussed the nucleus charge distribution, and we have concluded that somehow the charge distribution inside the nucleus is uniform, and but in some cases nuclei tends to possess these quadrupole moments, and that is due to the deviation from the spherical symmetry of charges. So we will discuss these moments due to the various charge distributions inside the nucleus. In this course, we are following the book Introductory Nuclear Physics by Kenneth S. Crane, 3rd edition. In this lecture, I have taken some of the illustrations from this book. Okay, if you remember, in my last lecture, I have discussed the nuclear magnetic moments, and there we have discussed the electromagnetic aspects of the nucleus, and there we have discussed these things, that much of what we know about nuclear structures come from studying not the strong nuclear interaction but instead the much weaker electromagnetic interaction. That is, we probe the nucleus through the electromagnetic, the tools which are based on electromagnetic interactions. That is, the strong nuclear interaction establishes the distribution and motions in the motion of the nucleons, that is proton and neutron inside the nucleus, and then we probe that distribution with the electromagnetic interaction. So the advantage of such probe which are based on electromagnetic interaction is that our measurement do not seriously distort the object we are trying to measure, that is the nucleus mass distribution that is there, and also the charge distributions. So we have discussed these things in the previous lecture as well, and here today again we are discussing the electromagnetic aspects of the nucleus. So in that regard, we will be using this electromagnetic based interaction. And we have also discussed that generally in electromagnetic theory you learn that any distribution of electric charges and current produces electric and magnetic field that vary with distance in a characteristic fashion. In the last lecture 14, we have discussed the current distribution, or we can say the motion of charges that give rise to magnetic moment, and we have discussed that with respect to the nucleus. And today we will be talking about the electric charge distribution, since the nucleus contains protons which are charged particles, and the distribution of those protons can give rise to quadrupole moments, and that exists only once there is deviation from the spherical symmetry of charges. So that we will discuss here in this lecture. So again, as we have discussed that these charge distribution give rise to fields which vary in a characteristic fashion, so it is important to assign the charge and current distribution multipole moments associated with each characteristic spatial dependence. And that is, if you remember last time, we have discussed these three things that we'll discuss this once we are talking about the quadrupole moments. That is, the field, the electric field arises from a net charge which we can assign the zeroth or the monopole moment varies as 1 over r. If you remember, spherical charge distribution possesses electric field which varies as 1 over r square. Now, if the charges are placed in such a way that we have positive and negative charges separated by a small distance, that is dipole, the electric field varies as 1 over r cube. And if the distribution is such that the field varies as 1 over r4, then we say that is because of some quadrupoles. Now, if you see the last slide, I told you that various charge distribution produces fields that varies in a characteristic fashion. So in this we'll be talking about the quadrupole moments, and if you just remember, we'll just summarize those things what you have done in the electromagnetic theory course. That is, if you have some charge distribution, the volume charge distribution, and you want to find out the electric or we can say the energy that is due to the electric quadrupole moment, then the potential, or we can say the energy associated with the charge, can be described as this volume charge density divided by d. That d can be expressed in terms of these r 1 minus r, that is the separation, and this is the volume charge density and the integral over this entire volume. So this gives you the potential due to these volume charge density. Now, if you remember, then you will expand the integral in power series in 1 over r1 by expanding this 1 over rd in a Legendre polynomial series. That is in a convenient way to express these things, 1 over d given by 1 over r times this Legendre polynomial series. And then you have these P0, P1 and P2 expressed in this fashion, and then the potential can be expressed in terms of these coefficients, where some of the coefficients are representing the total charge and some are representing the moments, as we have discussed the zeroth order moment, the first order moments, and the second order moment, or we can say zeroth, first and second moment of these distribution. So there we have the zeroth order as we can say the monopole, the first one is the dipole, and the second one is the quadrupole, and also you can extend these coefficients by expanding this summation. So why we are showing this thing here in the nuclear quadrupole moment, that is, we will be using this factor, this term. You need to remember this thing. On the coming slide we will be using this frequently, this 3z square minus r square. Now here this is the dipole, sorry, the monopole, this is the dipole, and this is the quadrupole. This q represents the quadrupole moment. If you just solve this integral, so that this will give you the total charge E, and this 1 over 2 comes from here, and this integral 3z square minus r square will give you the quadrupole moment capital Q. So you need to remember this 3z square minus r square, which arises in the second moment of this Legendre polynomial expression based for the potential due to volume charge density. So we'll be using this. Now the first thing is that why we are not talking about this electric dipole here. So since we are discussing the nucleus, so nucleus contains all the protons, and we don't have any distributions of protons such that it can give rise to these dipole moments, since for dipole it is required that the two charges should be of opposite polarity. So that's why this will not be in our discussion. And once we have a spherical symmetry, that is the charge distribution is uniform, we'll be having a spherical distribution, and once there is a deviation, so it will give rise to the quadrupole moment instead of the dipole, since dipoles are not there inside the nucleus, since whatever charge inside the nucleus is totally positive. So based on these descriptions that you learned already in your electromagnetic theory course, we'll be using this for the nucleus. So as I have discussed the expression for a spherical charge distribution, suppose that the nuclear charge has a cylindrical symmetry about an axis along the nuclear spin, and these are the various coefficients of that expression for the potential, such that I have discussed that this is the monopole, the dipole, and the quadrupole, and we will be focusing this thing. Now in that expression, based on this figure, if you make this x equal to y is equal to z, and that will be equal to r square by 3, if you just put that over here in this expression, if you just make this z square equal to this r square over 3, so in that regard this q will be 0, because this will be r square over 3, that 3 will be cancelled out, and then r square and r square will be cancelled out. So the quadrupole moment is 0 once we have spherical symmetry, that is x square equal to y square equal to z square. So in that regard we will not be having any quadrupole moment once we have spherical symmetry possessed by those distributions, and those distributions are discussed inside the nucleus, that is the nucleus the nuclei charge, or we can say that the proton charges are distributed in such a fashion that it possesses that spherical symmetry. Now if this 3z square is greater than r square, that is this factor 3z square is greater than this r square. So in that regard overall this factor will be positive, so we will be having a quadrupole moment which is positive. And similarly, if this 3z square again, this 3z square is lesser than this r, and we will be discussing this on the coming slide, what is meant by these r's, then this expression will yield a negative quadrupole moment. And in all these three limits, the shapes are given, that is, once we have spherical symmetry, so that there is no deviation from the spherical charge distribution. And if you remember, in the first part of the course we have discussed that the nucleus charge is somehow uniformly distributed, possesses that spherical symmetry. So most of the cases the quadrupole moments are 0 once we have this symmetry. And if this is greater than that is this, if this condition in this equation, if this for the second situation, that is 3z square is greater than r square, so that give you a positive quadrupole moment, and the shape is the prolate. And this one generally we have the spheroidal shapes, or we can have the surfaces are the charged surfaces. Now, so we have oblate and prolate shapes once we have these two situations, that is some deviation is there from the spherical symmetry, so it gives rise to these non-zero quadrupole moment. In the first case you have negative, and the second we have a positive quadrupole moments. So these are the limits one can discuss based on these quadrupole moment expression that we have taken from the electromagnetic theory. Now, so one can say that the nuclear electric quadrupole moment is a parameter, that is we have represented that by capital Q, which describes the effective shape of the ellipsoid of nuclear charge distribution, as we have discussed the three situations. Now, a non-zero quadrupole moment Q indicates that the charge distribution is not spherically symmetric, as we have discussed on the previous slide. By convention, the value of Q, which is the quadrupole moment, is taken to be positive if the ellipsoid is prolate, and negative if it is oblate. As on the previous slide we have discussed that once we have deviation for the spherical symmetry, so that the quadrupole moment will be there for the nucleus. So how these quadrupole moments are then discussed are what are those parameters which can give rise to these deviations. Those we'll be discussing in this lecture. Now, the first thing is that all these descriptions that we have done so far, taken from the classical electromagnetic theory. So, since once we are talking about nucleus, so there we will be using the quantum version of these quadrupole moments, or we can say those electromagnetic moments, or we can say the fields associated with the charge distribution. So in quantum mechanics, electric quadrupole moment is determined with respect to the probability density, that is psi naught square. Now, if you just remember the previous discussion, that this QE is the quadrupole moment, this E is the charge on the proton if we are talking about the nucleus, and this Q is the quadrupole moment, and that will be related, or we can say linked or equal to this expression. Now, if what is this 3z square minus r square is the same expression for the quadrupole moment, and we will be using in quantum mechanics an operator form, and that relate with the probability density. Now, what we are doing here in the nuclear regime using quantum mechanics, by treating multipole moments, that is 3z square minus r square in operator form, and calculating their expectation values for various nuclear state, and then these expectation value can be directly compared with the experimental values we measure in the laboratory. You can need to look for the experimental setups for calculating the quadrupole moment and the magnetic dipole moment for various nuclei in chapter number 16 of your course book. So this is the mechanism through which these quadrupole moments of various nuclear states can be calculated by just calculating the expectation value by treating this as an operator form. But remember, in quantum mechanics, you know that once you have a scalar operator, so then you can combine this psi star and psi, so that this give rise to the probability density psi mod square. Once this is in a scalar operator. Now, so in that way, the quadrupole moments EQ of a classical point charge E is of the form E3z square minus r square. Now, if the particle moves with a spherical symmetry, we have discussed this thing in the introduction part, but we are just repeating it in the quantum version as well. Once we have a spherical symmetry, then the quadrupole moment vanishes. If a particle moves in a classical flat orbit, say xy, such that z is equal to 0, then q will be equal to this minus r square. That the quadrupole moments in quantum mechanics is given by this, as we have discussed. So you can find out these limits again, that if you just put r square over 3 over here, again this will vanishes, since I told you that this will be a scalar number. So you need to just make this out of the integral, and then calculating, this will be r square. For the spherical symmetry case, this will be 0. That is for a single proton. For an orbiting neutron, this q equal to 0. Now this is the expression. If you remember, we have discussed the three limits of the quadrupole moments in the introduction part. So this psi square is spherically symmetric, then q is equal to 0, and then you need to use all those condition we have discussed, that is this z will be equal to z square will be equal to r square over 3. Now this is, if z is equal to 0, that is an xy plane, so this will be see this, there is a deviation. If you remember the two cases, the two spheroidal shapes that we have discussed, the prolate and the oblate form. So in those situations, you have deviation from the spherical symmetry, and these numbers can be directly obtained by using the values, the input values over here, and then q will be of this order, and also it will be equal to q is equal to +2, and then what is this r? This r is the mean square radius of the orbits in which the nucleons, or we can say the protons, are orbiting. So that the details of these things can be understood once we complete the nuclear shell model, and then we'll be using this effectively, how these quadrupole moments and magnetic moments are helpful in locating, or we can say discussing the various aspects of the nucleons inside the nucleus. Since in this part of the course we are talking the fundamental properties of the nucleus, so we have discussed the charge distribution, the mass distribution, how one explores the nucleus, and then the various models, and then the various electromagnetic moments of the nucleuses. So once again, the pairing force is helpful, as we have discussed in the semi-empirical mass formula. If the paired nucleons move in spherically symmetric orbits, they do not contribute to the quadrupole moments. Once there is deviation, so then we will be having a non-zero quadrupole moment. But this is a rough statement. At the end of this lecture, you will see that this is not the case always, that only the unpaired nucleon can give rise to these moments, but the situation is somehow complicated. We might therefore expect that for many nuclei, the quadrupole moments can be estimated from the valence nucleons. As I told you, this is not always the case, but which can be assumed to orbit near the surface, so that r is equal to r naught a to the power 1/3. For this will be valid since this is the size of the nucleus, or we can say radius of the nucleus. So those nucleons which are once we are talking about valence nucleons, so that the r will be equal to r naught a to the power 3, because that will be orbiting far from the center of the nucleus. So for that, if we use r equal to r naught a to the power 1/3 for valence nucleons, so in that regard the quadrupole moment, which by definition equal to EQ, equal to, we need to put E, the charge, so that dimensionally it is correct, and for the for the valence nucleons we need to put, instead of r, this r naught a to the power 1/3, and since this will be square, so that this will be r naught square a to the power 3, which ranges from about 610 to the power minus 30 eV square for light nuclei to 50 for heavy nuclei. This number we will be discussing for measuring the nuclear cross section. Also this is important, but also once we are talking about quadrupole moment, this is also a handy number to work with the quadrupole moment. The range lies in this 6 to 50 10 to the power minus 30. As I told you, it is not always the case that these valence nucleons give rise to the quadrupole moments. Now the unit of 10 to the power minus 38 meters square is used frequently in nuclear reaction studies for the cross sections, and also it is known as the bonds. So the unit is also convenient for measuring the quadrupole moment. Thus the expected maximum is from this to this, as we have discussed on the previous slide, and this is the table taken from your book. And you see many nuclei do fall in this range, but several, especially the rare earth regime, are far outside, that is in this range. The sum of the number are very large, so that the statement that only the valence nucleons contribute to the nuclear quadrupole moment, that is somehow complicated. Here the quadrupole moment is giving an important information, that is, the model of the single particle cannot explain the large observed quadrupole moments, as we have discussed for the rare earth regime. That is, these quadrupole moments cannot be found out once we are talking about single particle, that is the unpaired nucleons. So most or all of the proton must somehow collectively contribute to have such a large quadrupole moment. That is, once the number is large, so it is not the valence, or we can say the unpaired nucleons, which can give rise to this quadrupole moment, but they must somehow collectively contribute. That is, every nucleon contribute to such large Q values, that is the quadrupole moment. Now, so based on this observation, the assumption of the spherically symmetric core of paired nucleons, that is, the paired nucleons which are lie at the core, that is, they are paired, is not valid for these nuclei. As I have told you, that the statement that while valence nucleons contribute to the quadrupole moment is somehow contradict to these large quadrupole moments, so that somehow collective contribution give rise to such large quadrupole moments. Now you need to remember the quadrupole moment arises due to the deviation from the spherical symmetry of charges. Now the core in certain nuclei can take on a static non-spherical shapes, then that can give a large quadrupole moment. If you remember, in the introduction part we have discussed these quadrupole moment, or we can say the non-zero value of the quadrupole moments are related with the deviation from the spherical shape, that is the oblate and the prolate form, and that can be achieved in certain the core in certain nuclei as well, so that it give rise to these large magnetic electric quadrupole moment. So if we conclude that in the first part of the course that nuclei charge distribution is somehow uniform, that is for some cases there is deviation from the spherical symmetry, and it can give rise to non-zero quadrupole moments. So with this, I thank you for your time.